Hello dear friends, we continue our discussion on the branch and bound algorithm, and today I'm going to solve another example with branch and bound algorithm for binary decision variables. So let's get started. The example that we are going to solve is given in this way. So this way makes us gives us an opportunity to illustrate the use of the branch and bound algorithm. In real life, of course, you will not be able to obtain such a table. Okay, this table is if you have this table, it means that you already know the optimal solution. So this is just for illustration purposes. Okay, no one will give you such a table in real life. Okay, let's first understand this. And what we are going to do is we are going to solve an optimization problem, which is a maximization problem. It is given as a maximization problem. Okay, and it's a mixed integer programming formulation in which x1, x2, and x3 are binary, but x4 is a continuous decision variable. Okay, so we should be careful. We must be careful with x4. We are not enforcing x4 to be 0 or 1 or an integer value. It's greater than or equal to 0. It's continuous. Okay, so in this table, all the solutions for all possible LP relaxations are given to us. Let me explain it in more detail. So look, the first column here represents x1 variable. The second one represents x2 and the third one represents x3. x4 is not here because it is continuous, it is not integer. Okay, last time in our previous example, I told you that if a variable is free, it is not fixed to take a value of 0 or 1, then we represent it with this symbol. So in this first row here, you see x1 is free, x2 is free, and x3 is free. And let's remember what free means. Free means we relax the value of the variable. So in this case, relaxing means having this, for example, x1 between 0 and 1. Okay, like this, in between 0 or 1. Okay, so let's have a look what else we have here. x1, x2, and x3 all are free in this first row. It means that the first row is the LP relaxation of the original model. All decision variables are free, none of them are fixed, and this is the LP relaxation, which means that in our branch and bound algorithm, in fact, this is the root node, right? All decision variables are free, they are continuous between 0 and 1, and x4 is already continuous. So this is the LP relaxation, and this is node 0, root node. Okay, and the solution is given here in the fourth column of the table. This is the solution. Solution of what? This is the solution of the LP relaxation. Okay, what do you obtain when you solve? x1 becomes 0.2, x2 is 1, x3 is 0. So these are the binary decision variables. And x4 is equal to 0. It's a continuous decision variable, but it appeared to be 0. And the last column gives us the optimal objective function value. So the LP relaxation has an objective function value of 82.8. Okay, let's look another row to another row randomly. For example, this one. In this row, you see x1 is free. x2 is set to 1, so it's not free, it's fixed to 1. x3 is free. And when you solve this problem, you see that x1 appeared to be 0.2, x1, x2 is 1. Because it's fixed, its value should be equal to 1. Okay, then x3 is 0 and x4 is also 0. And the objective function value for this solution again appeared to be 82.8. And you see in this table, we are given all possible combinations for these fixed and free decision variables. Okay, fixed to 0, fixed to 1, or free. So each variable in fact has three alternatives, either fixed to 0 or fixed to 1 or free. And since there are three such variables, binary variables, then we have 3 times 3 times 3, 27 possible combinations, and in this table you will see all those 27 combinations. Their solutions are given and their objective function value are given. As I said, this is just for illustration purposes, how to sketch the branch and bound algorithm. Okay, so we are going to use this table to solve this problem. This is the maximization problem. Okay, and we will solve that problem. So sometimes, while illustrating this branch and bound algorithm, we can enforce additional conditions, additional rules on the branching or selecting the alternatives during the branch and bound. In this way, the solution of the branch and bound algorithm, or the branch and bound tree, whoever follows these rules should be identical to the other one. Okay, so what are these conditions? For example, the first one says use depth first search. We now know what depth first search and breadth first search is, and it asks us to use depth first search. Whenever there are more than one open nodes, open branches, we will select the one which is in lower levels, in the bottom levels. Okay, so we will use depth first search. But it doesn't solve alone all the problems. Okay, then we have this. If there are, if we are going to branch, so when we branch, in fact, a node, what do? On one side, we fix the value of the variable to 1, and on the other side, we fix it to 0. And which one to select? There are two open nodes now, and they are at the same level. So which one should we select first? And this says that, okay, if they are in the same level, first select the node which fixes the value of the variable to 1. Then after evaluating this node, go to the other one and evaluate the node which fixes its value to 0. Okay, and this also, these two conditions also is not enough. We may have other alternatives and need to make some selections, and we need one more rule, and that is this. If more than one non-integer variable exists in a solution, okay, then which one we should select for branching? And this rule says that branch the integer value which is closest to the integer. Branch on the variable whose value is closer to integer. Let me give you an example. Let's assume that we have a solution in which value of x1 is 0.2. Okay, value of x2 is 0.5. Okay, and value of x3 is 0.8, let's say. Okay, so we have such a solution. Remember, in this question x4 was continuous, so we don't need to consider its value. So there are three alternatives in this solution. Which one should we select first, so that while branching, which one should be fixed first, x1 or x2 or x3? According to this rule, it says that select the one with the value closer to integer. Then we need to look, okay, this 0.2, the value of the first decision variable. It is closer to 0, right? 0 is an integer value. It is closer to 0, and the difference from 0 to 0.2, it's just 0.2. Okay, this is 0.5, the second variable x2, and it is from 0, the distance is 0.5, and from 1, the distance is 0.5 again. So 0 and 1, these are the integer values, and we need to look at the difference between these values and the closest integer. Okay, and this one is the distance of x2 to the closest integer is 0.5. What about this? 0.8. So it is closer to 1, right? The integer value. And the distance of this x3 to the closest integer is 0.2. Okay, now we know that according to this rule, we will not select x2 because it's not too close to an integer. But we need to select either x1 or x3 because both of them have the same distance to an integer value. Okay, the second part of the rule says that break ties by choosing a variable with smaller index. Okay, so tie means equality cases. If two alternatives have exactly the same distance, then we should select the variable which has a smaller index. Okay, let's remember this is x1 and the index of this is 1, and this is x3 and the index is 3. So in order to break this tie, this equality, I would select x1 because its index is smaller than the other one. So I will first branch on x1 according to this rule. Okay, so basically these are the three rules that we are going to use in solving this problem. So okay, I'm going to solve this problem again on this sheet of paper. For that purpose, I reduced this table a little bit and placed it on the corner. Again, on my paper, I have this table so that I will write the lower upper bounds and the gap values to here. At each node, I will write their values here. Okay, so what do we do? For the branch and bound algorithm, we start from the root node. Root node is the LP relaxation. And as I said, that in LP relaxation, all decision variables are free. So the first row in this table is the solution for the LP relaxation. Okay, so let me sketch the branch and bound tree to here. So we will first have node number 0, which is the root node. And in this root node, in fact, we are solving this problem. The first variable is free. Second variable is free. Third variable is free. I don't need to write the fourth variable because it's continuous. Okay, so only x1, x2, x3. And when I solve this problem, I get the solution. Again, we can write the solution as x0. Remember, sometimes we put a tilde on it. So it's just the solution of this LP relaxation. And from the table here, the solution is given here. X1 is 0.2. Okay, 0.2. X2 is 1. X3 is 0. X4 is 0. Now in the solution, I am writing the value of x4. Here I don't have x4, but in the solution, I need to write the value of x4. Okay, that's important. And the solution value, so in the table, it's written as v. Okay, we usually write the objective function as z. So it's not important, it's just a notation. So if you like, you can write z. If you like, you can write v. It's not that important. And this value is 82.8. Again, in the table, it's written as tilde. It's not important. It's just a notation, okay? Then this is the solution, what we have in the root node. And now we need to make a decision. Can we fathom? By the way, sometimes we can fathom even in the first node. Okay, we don't branch at all and we fathom here. And what may be a reason? Think about the three reasons. Fathom because of infeasibility, fathom because of optimality, fathom because of bound. Okay, so what can be a reason to fathom here? If the LP relaxation is infeasible, you fathom. Okay, it can be a reason. Secondly, if you solve the LP relaxation and obtain a completely integer solution, then you can fathom without any branching. And finally, sometimes for some problems, we have an integer solution. We already have an integer solution. Okay, and we know its value. And when you solve this LP relaxation, the objective function value that you obtain here, if it is exactly the same, this is the upper bound, remember, if it's exactly the same with your integer value, then because of bound, again you can fathom. Okay, these can be the reason for fathoming even in the root node. But here, can we fathom? This is a maximization problem, and initially, remember, we set the lower bound value for a maximization problem to minus infinity since we don't have any integer solutions. And the objective value of this solution is 82.8. We cannot fathom because of infeasibility because it's feasible. We have a solution. We cannot fathom because of solving because x1 value is non-integer. And we cannot fathom because of bound because the solution that we obtained here is better than our lower bound. So we need to branch. Okay, so branching should be done by dividing this into 2 and branch on which variable? It should be a non-integer value. And you see x1 is the only non-integer value, which is 0.2. So I need to branch on x1. Again, you can write this to either side. It's not important. You can write x1 equals to 1 here and 0 here, or vice versa. x1 equals 0 here and x1 equals 1 here. It's not important. But be careful. Sometimes some of your friends do this mistake. They say that, okay, I'm writing x1 equals to 1 here, and on the other side, they write x2 equals to 1, another variable. No, the branching is done always on the same variable. Okay, and if it's the binary variable, we fix the value of that variable to 1 or 0. Okay, on one side it's 1, on the other side it's 0. Now we have two open nodes. Okay, after our decision, after solving this LP relaxation, let's write what happens in node 0, root node here. The lower bound, since we don't have any integer solution, the lower bound is minus infinity. So always, while considering this lower and upper bounds, you need to think about, is this a minimization or a maximization problem? Ours is a maximization problem. And an integer's feasible solution for a maximization problem gives us a lower bound. And where shall we find the upper bound? We will find the upper bound either from this root node, which is the LP relaxation, or we will find from the parent bounds, okay? Parent bounds. The open nodes are these two. We haven't solved those yet. And the parent of these is the root node, and the value of the root node is 82.8. It gives us the upper bound. Okay, so it's 82.8. And I said that we calculate the gap value with the formula best possible minus best found divided by best possible. Okay, numerator is in absolute value, and we multiply this by 100 to find the percentage. But at the beginning of the branch and bound algorithm, if we don't have any integer feasible solution, in a maximization problem, the lower bound will be minus infinity, In a minimization problem, the upper bound will be plus infinity. And in that case, if you try to calculate the gap value, it will be infinity or something undefined mathematically. That's why we don't write the gap value until we find an initial feasible solution. Okay, now we have two open nodes and we will continue with the branch and bound algorithm, and the algorithm says that select one of the open nodes. Now we need to look at our rules, which one to select. We will use depth first search, but they are already in the same level. Okay, so this is level 0, this is level 0, and this is level 1, and both open nodes are in level 1. So depth first search does not tell me anything about which one to select. And there's another rule that I already written. It says that if the open nodes are at the same level, then select the one which fixes the variable equal to 1. Okay, so on this side it's fixed to 0, on this side it's fixed to 1. So according to that rule, I have to select this one. And as soon as I make the selection, I put the number on it. Okay, so these node numbers should be written in sequence. You do not just write 1, 2, 3 randomly. Okay, it shows you the sequence of evaluating these nodes. Okay, now we will look at the table for the solution of this problem. But first we need to write what is the problem here. What are we solving? Okay, what did we do here? We fixed the value of x1 to 1. It means that x1 is fixed to 1, x2 is still free, and x3 is still free. Okay, we are solving this problem, and for the solution of this problem, we need to look at the table. So if you look to this row here on the right hand side, x1 value is 1, x2 is free, and x3 is free, which is this one. Then the solution, so I'm going to write x1, the solution, 1, 0, 0, 0. And the objective function value of this solution is 74. Good. Now it's time to make some decisions and some conclusions. Can we fathom? And it's obvious that we can fathom because all decision variables x1, x2, x3, all of them 0 or 1. So we fathom. And the reason of fathoming is by solving. Sometimes instead of fathoming, they may say cutting, cut the branch of the tree. Or sometimes they say terminate the node. By solving or by optimality or by finding an integer solution, all of them are the same, have the same meaning. Okay, good. We fathomed this, but since this is an integer feasible solution, since we found an integer feasible solution, I need to consider what happened to my incumbent solution. Remember what was incumbent? Incumbent. It is the best integer solution that you found until that point. Since this is an integer solution, I need to check, should I update my incumbent or not? And initially, my incumbent value is minus infinity, the lower bound. And when I come here, I am trying to maximize. I have a solution with an objective value of 74. Previously, I didn't have anything. It means that I need to update. So my incumbent becomes equal to 74. Since I updated my incumbent, I put a star here because at the end of the algorithm, when the algorithm stops, in order to find what is the optimal solution, I will check the nodes with a star. Okay, these nodes with a star will give me the optimum solution. Okay, now we can fill in our table since we concluded with node 1. In node 1, the lower bound Now it's updated to 74. And the upper bound is the for calculating the upper bound in a maximization problem, we need to check the open nodes and we need to find what is the best possible value that we can obtain from here. And for that purpose, we need to look at the parent of this. And the parent tells us that you can obtain 82.8. This is the best that we can get. Then the gap value will be 82.8 best possible minus 74, which is the best found. Best possible, best found. Found means an integer solution divided by best possible. And in this case, best possible is 82.8. So it is upper bound minus lower bound divided by upper bound. So for maximization and minimization, there is a difference here. Okay? And we multiply this by 100 to find its percentage. And it makes 10.6%. Okay, so you see, initially we didn't have a gap value, but as soon as we have a lower bound, the lower bound is updated, we calculated the gap value, and this 10.86 tells us this, the information that we can get from 10.6% is this. We are in the worst case away from the optimum solution by 10.6, at most 10.6. Okay, so this solution that we found here, 74, in fact can be the optimal solution, but we don't know it yet. At the end of the algorithm, when we evaluate these nodes, maybe we will not be able to find a better solution. Then this solution will be our optimum solution. But at this point, we don't know it. Okay? So, but what we know is, at this point, if you stop the algorithm and if you decide to use this solution, it is worse than the optimum solution by at most 10.6%. At most. It's the critical word here. At most 10.6. Okay, let's continue. The next node, there's only one node, so there is no selection here. I will just number it as 2, and I'm going to solve this problem. And what problem is it? Again, let me write. I fixed x1 equal to 0, x2 is free, x3 is free. And now I will look at the table. You see, how are we using the table? We are just identifying which problem we are solving at each node. And then we go to the table and find that row. Okay, find that row. And then we find the solution. Okay, the solution is given here. I'm going to write x tilde 2 here, and its value is 0, 1, 0.67, and 0. And the z value is 80.67. Okay, good. Now it's time to make the decision. Can I fathom? Can I fathom because of infeasibility? No. Can I fathom because of integer solution? No. X3 value is 0.67. And can I fathom because of bound? As I said, you need to be careful with the bound. Okay. What is the best solution? Best integer solution, that is the incumbent solution that you have until now? It's 74. And if you continue branching on this node, what is the best possible value that you can obtain? It's 80.67. So there is a possibility that you can obtain a better solution. So you cannot fathom because of bound. It means that you need to branch. Okay, let's branch. this, and this. Okay, so if you look at the decision variables, we have x1 is already integer, x2 is already integer, x3 is the only non-integer variable. So we will fix x3. Again, I'm going to fix its value to 1 and to 0. And now we have two open nodes, and we can write what happens to node 2 in our table. What's the lower bound? Lower bound is the incumbent best integer solution. It's still 74. What about the upper bound? The best possible. Okay, for the upper bound, you need to look at the parents of the open nodes. And the parents of the open nodes is node 2, and its value is 80.67. So the best that you can obtain is 80.67. It means that your gap value should be 80.67 minus 74 divided by 80.67 multiplied by 100, and it makes, if you calculate, 8.3%. Okay, now look what happened. From in node 1, the lower bound is updated from minus infinity to 74. The upper bound was the same. So your gap value reduced. As I said, gap value always reduces or stays the same. So even if it's a maximization or minimization, it doesn't matter. It always either stays the same or reduces. Okay, so initially when we write this sign here, it means that your gap value is infinity, in fact. Okay, from infinity you reduced its value to 10.6 by updating your lower bound. And here from node 1 to 2, what happened? Your lower bound is the same, but your upper bound reduced, and that's why your gap value is changed from 10.6 to 8.3. It's again reduced. So your gap will be reduced if your lower bound is updated. It means that you found a better integer solution, or your upper bound is updated. Otherwise, if your lower bound and upper bound are the same, then your gap value will be the same. When you solve your models problems in Cplex OPL, in the engine log tab, okay, if you go for engine log, you will see that in this tab, you will see all these lower bounds, node numbers, lower bounds, upper bounds, and the gap values as I am writing here. You can follow how the branch and bound continues here. Of course, in Cplex OPL, it is not just using the branch and bound, but it's continuing, or it's using the branch and cut algorithm. But still, the main idea, the main procedure is similar. We will talk about branch and cut later on. Okay, now let's continue with the algorithm, and now we have two open nodes. We need to select one of them. They are at the same level according to depth first search. I cannot make a selection, but our rule says that always select the branch which fixes the value of a variable to 1. Okay, so we are going to select this as our third node. And now I need to write what is the problem that I am solving here. For that reason, you need to follow the path from this node up to the root. And here we fix the value of x1 equals to 0. And here we fix the value of x3. It means that x2 is still free and x3 is fixed to 1. So we are solving this problem, 0, free, 1. And now it's time to look to the table 0, free, and 1. It is this row here. So the solution is, let me write x3 tilde 0, 0.810 with objective function value equal to 79.4. Okay. Now I need to make a decision about this node. Shall I branch or fathom? And if you look, you cannot fathom because of infeasibility. You cannot fathom because of integer feasibility because x2 is non-integer. Can we fathom because of bound? For that purpose, you need to ask what's your incumbent. Your incumbent is still 74. You can look to your table. Incumbent is 74. And the objective value here, 79.4. For a maximization problem, this is better than your incumbent solution. It means that you cannot fathom because when you branch on this and evaluate this, there is a possibility that you can find a better solution. Okay, so we continue branching. I need to branch this into two. Okay, let me write like this. And we are going to branch on the integer, non-integer variable, which is 0.8. Okay, so on this side, I'm going to write x2 equals to 1, and on this side, I'm going to write x2 equals to 0. So you see, in this example, we haven't encountered a case in which more than one decision variable to be non-integer at the same time. At each branching, at each case, only one decision variable appeared to be non-integer. But if two decision variables were non-integer at the same time, according to my rule, I had to select the one which is closest to integer. If both of them are same distance from an integer value, then I would select the decision variable with a smaller index. Don't forget that rule. Okay, now at this point, I can write what happens to node 3. My incumbent is still the same. It's 74. What about the upper bound? Upper bound comes from the parent of the open nodes. The parent of these two nodes is this one, and its value is 79.4. The parent of this open node is this one, and its value is 80.67. I am maximizing, so which one has a higher value? This one. So your upper bound is still 80.67. The lower bound is the same, the upper bound is the same. It means that your gap value will be the same. So 8.3%. It's not updated. Okay, now I have three open nodes. Which one should I select? You need to consider the rules. The first rule you should look is the depth first search. According to depth first search, you cannot select this one. You should select either this or this one because they are at a lower level. In the branch and bound tree, they are in lower levels. Okay. Okay, so which one of these two? And my rule says that select the node which fixes the variable to 1. So it means that this is node number 4. Okay, which problem I am solving here? Again, go back to the root node. x1 is fixed to 0, x2 is fixed to 1, and x3 is fixed to 1. So what problem I am solving? All variables are fixed. But remember, you have the fourth variable. Fourth variable is a greater than or equal to 0. What's its value? In order to find its value, you need to solve the model again. Okay? And how do you get the problem? How do you get this solution? Again, look at the table, and we will find this 0, 1, 1, which is this one here. Okay? So when you solve it, it is x4 tilde, and it has the value 0, 1, 1, and x4 value is 0.5, and z value is 77. Now I need to make a decision. I know that many students make a mistake here, and when I ask the question, shall I fathom or branch, they say that the x4 is non-integer, so we need to branch. But the thing is, in the question, x4 was a continuous variable. You should only consider integer variables. And if you look x1, x2, x3, all of them are integers. It means that you have to fathom this. And the reason of fathoming is by solving. Why I am saying solving? Because the objective value 77. What was our incumbent solution? It was 74, right? Now we found an integer solution. This is called an integer solution. Although this is fractional, it's integer feasible. Okay? So we found an integer solution with a better objective function value because we are maximizing. So I need to put a star here and I need to update my incumbent to 77. Okay, and the reason for fathoming is by solving. Then I can write, I can fill in my table. My lower bound is updated from 74 to 77. My upper bound, check the open nodes, the parents of the open nodes. From here 79.4, from here 80.67, so it should be 80.67. And the new gap value will be 80.67 minus 77 divided by 80.67 multiplied by 100. And if you calculate this, you would obtain a gap value of 4.5%. Okay, your gap is updated because your incumbent, your lower bound is updated. Now I have two open nodes. Which one should I select? According to depth first search, you need to select this one. So the next number that I need to use is 5. And what problem I am solving here? x1 is fixed to 0, x2 is fixed to 0, and x3 is fixed to 1. And the solution here, if you look at the table, 0, 0, 1 is this one here, and it writes infeasible. If you try to solve this relaxed model where x1, x2, x3 are fixed to 0, 0, 1, it's infeasible. And what shall we do with this node? The answer is easy. Fathom. Fathom by infeasibility. Okay. And now I can fill in my table, which is node 5. Your incumbent solution is still 77. What about your upper bound? Upper bound comes from the parent of the open node, which is still 80.67. So the upper bound and the lower bound are the same. It means that your gap value is the same. I have only one remaining node, which means that I need to number that node as node 6. And what problem I am solving here? Again, you need to follow back to the root node. And you see x1 is fixed to 0, x2 is free, and x3 is fixed to 0. And when you solve this problem, x6 tilde in the table, 0, free, 0, where is it? This one. Okay, the solution is 0, 1, 0, 2, and your z value is, what is it? 28. Good. Now, what shall I do? All decision variable values are integers. It means that you have to fathom. And the reason of fathoming is, you can say by solving, since all of them are integers. But also, check this. Your objective value is 28 and your incumbent is 77. You are maximizing. It means that 77 is better than this one. So you can either write by solving or you can also say by bound. Okay. Then shall I update the incumbent solution? No, of course not, because this is not a better solution than your previous incumbent. So node 6, what happens to your lower bound? It's still 77. What about the upper bound? Since there are no open nodes, your upper bound should be equal to your lower bound, which is 77, and your gap value is 0. Whenever your gap value is 0, the branch and bound algorithm stops. Or whenever the algorithm stops because there are no open nodes, then your gap value should be equal to 0. Now we found the optimum solution. But what is it? So your lower bound here is your incumbent solution. So it is your optimal objective function value. What about the values of your decision variables? And in order to identify it, in this branch and bound tree, you need to go to the node with a star where you updated your incumbent, and you need to go to the last star. Okay, so the star or node with the highest node number, which is this one. This is also star, you see, but this has a larger number, and it means that your optimum solution is this. X1 value is 0, x2 value is 1, x3 value is 1, and x4 value is 0.5. Again, let me repeat, x4 is a continuous variable, so it can be 0.5, no problem, and your z star value is 77. So this is the example. Now, as an homework or as a practice, what you can do, let me tell you. Instead of depth first search, solve the same problem with breadth first search. Okay, so you need to find the same objective function value. Okay, you have to find the same objective function value, but your branch and bound tree may be totally different. It can be a larger one, it can be a smaller one. Okay, with breadth first search, what you can do, you can first go from the decision variable by fixing its value equal to 1. Okay, so this is one alternative. And then you will have a branch and bound tree. Or you can go first by fixing a variable value to 0. And you will come up with a different branch and bound tree. And also in depth first search, you can use, instead of selecting a node by equating its value to 1, you can select the opposite node by equating its value to 0. And again, you will end up with a different branch and bound tree, but the same optimal objective function value. So these are some practice problems that you can do by yourself to test if you understood it or not. And please try to fill in such table to understand the lower bounds, upper bounds, and gap values. Okay, filling in this table is very important. Final thing that I'm going to mention in this topic, in this lecture, is this. In this problem, we have 3 decision variables. Okay, so with 3 decision variables, let's start with this root node. In the first level, let's assume that we fix one of them just randomly. One of them to 1 or 0. So let's say x1 equals to 1 and x1 equals to 0. Okay, then in the next level, let's fix the value of x2. So I'm going to do like this. Okay, x2 equals to 1 and x2 equals to 0. And here, x2 equals to 1 and x2 equals to 0. Okay, and then in the next level, let's say that x3 equals to 1, x3 equals to 0, x3 equals to 1 here, x3 equals to 0 here, x3 1, x3 0, and x3 1 and x3 0. Okay, so each one of these final nodes tells us a different solution. For example, here x1 is 1, x2 is 1 and x3 is 1. Here x1 is 1, x2 is 1, x3 is 0. 1 0 1, 1 0 0, 0 1 1, 0 0 1 0, okay, 0 0 1 and 0 0 0. So these are the all possible combinations of these decision variables. In fact, with this branch and bound tree, we are trying all possible combinations. But at some point, when, for example, we try this node and try to solve this LP relaxation at this node, and due to some reason, because of infeasibility, because of finding an integer solution, or because of bound, we decide to fathom. Okay? When we fathom this node, it means that we eliminate checking all these solutions. By just cutting, terminating from here, we eliminate all these, and it saves time for us. Remember, at the beginning I told you in the lecture that if you try to solve a problem using complete enumeration or total enumeration, it will take a lot of time. In fact, in branch and bound algorithm, we also make such an enumeration, but we make it in an intelligent way so that by cutting, by terminating some of the nodes, we eliminate the total number of branches, total number of solutions that we are trying. And it saves time. Again, let's assume that you fathom this node. So whenever you fathom, you eliminate these ones. Okay? So instead of trying all these combination solutions, by just trying these, you end up, or you find the solution. And this reasoning is, in fact, tells you why with this branch and bound algorithm you get the optimal solution, because in fact you are checking all possible combinations with this algorithm. So you are checking all possible combinations in an intelligent way, and at the end of the algorithm the solution is exactly optimum solution. Okay, so this is the end for this lecture. Thank you very much for listening. Please make these practices by yourself to improve your understanding.